Welcome to topic 4, in which we're going to think about the rotational constant and angular momentum. So we've already seen the expression for the rotational energy, which comes out from solving the Schrödinger equation, so with rotational quantum number J, and this is in joules. If we now express the energy as a wave number, so basically we divide the energy by hc, where h is Planck's constant and c is the speed of light in centimeters per second. This gives us what's known as the rotational term, f of j. So we can write it like this. And this is now a wave number and has units of centimeters to the -1. You'll note that all these numbers here, all these terms, are actually constants. So if you have lots of constants, what we often like to do is group them together into a new constant, and here we're going to call it B. And B is the so-called rotational constant, and it has units of centimeters to the -1. The rotational constant is a constant for a given molecule, and you can look it up in tables or you can calculate it yourself. Let's now move on to think about angular momentum a little bit more. In the same way that you have linear kinetic energy, so ½ mv squared, we also have rotational kinetic energy, and this is given by a ½ I omega squared, where I is the moment of inertia and omega is the angular velocity. We also have an angular momentum in parallel to the linear momentum that you will have already seen. So angular momentum P is equal to I times omega. So I is the moment of inertia, omega is the angular velocity. We can combine these two equations to give us this expression here, which gives us the angular momentum as a function of the rotational energy. But we know from solving the Schrödinger equation for rotations that the energy is quantized. And if we look at this expression here, which has energy in, we can therefore deduce that the angular momentum is also quantized. So let's think a little bit more about the quantization of angular momentum. If we now work together with these equations, sort of follow everything through, we can find out that the angular momentum P is quantized and depends on the quantum number J according to this equation, where J, of course, is the rotational quantum number, which takes values of 0, 1, 2, and so on, and h bar is Planck's constant h divided by 2 pi. Again, this is something that you should be able to work out and show. It goes further than this, though. So once we have the angular momentum, quantum mechanics actually says that the angular momentum can only point in certain orientations in space. So here we have the z component of the angular momentum of a state with quantum number j is given by mj multiplied by h bar. Mj is another quantum number, so if you like, it's the magnetic angular momentum quantum number, and it takes values from -j to +j. So this means that if we have j equals 1, possible values of mj are -1, 0, and +1. So the state is therefore threefold degenerate. We can represent it in a picture like this. So we have, from a classical perspective, 3 orientations of the angular momentum of the system. In general, rotational states have a degeneracy of 2j + 1 for a quantum number j. So if you know j, we know the degeneracy of the rotational state. And this has big impacts on the appearance of a rotational spectrum, which we'll come on to later. Okay, so homework for this topic is to use the expressions for energy and angular momentum that we've seen in this topic to show that Pj is equal to h bar square root of j, j + 1.